Okay, I think it's recording now. Okay. Hi, everyone. Thank you for joining our second webinar of this year, hosted by ISIE Student Chapter Board. This session's titled is Standards for Industrial Ecology, Methods and Their Applications. We are honored to have two distinguished professors who will share their expertise and insights with us on this important topic. So I'm going to briefly introduce our two speakers. Professor Joule Bergerson is from University of Calgary. Her research focuses on system-level analysis for policy and decision-making, particularly the developments of tools and framework to assess emerging technologies and their policy implications from life cycle perspective. Our second speaker is Professor Stefan Pauliuk. He is from University of Freiburg in Germany. He is an expert for method development to assess sustainable development strategies. He works with supply chain analysis and scenario modeling for sustainable material futures. We're thrilled to have both of you join us today. And we have 10 audience now. So for our audience, feel free to post your questions in the chat at any time or use the raise hand feature if you would like to unmute and ask questions directly. We will have our Q&A session at the end after two presentations. So Stefan, would you mind start us off?
Mengqing, thank you for the nice introduction and for inviting us for organizing this seminar. I'm happy to start and happy to be part of the crowd today. So usual procedure, sharing the screen, switching to the presentation mode, and then happy to get started. So my name is Stefan Pauliuk. I'm a professor at the University of Freiburg in Germany, and my focus is on scenario modeling for material cycles, focusing on supply and demand side solution and increasingly also moving into consumption corridors by by considering inequality. Today, I want to talk about something else. I have structured my contribution into two topics. First, a general notion of the indicators that we need to measure the material implications of sustainable development, and then a specific case study reviewing a circular economy standard from the British Standard Organization on the circular economy in organizations. So we know we need materials for a lot of stuff. Here we have the different SDGs that again have more than 200 specific indicators for human development, both in the global south and global north. And those SDGs with black boxes are directly related to materials. For example, SDG number 9, for industry and infrastructure, we need materials to actually build the infrastructure. So it's crucial, the materials. Materials pose major sustainability challenges. They are at the basis of modern urban expansion, and the consequence is we need a lot of them. So the two bulkiest materials, cement and steel, we produce millions of tons of them, 11 million tons of cement, 5 million tons of steel, not per year, but per day globally. So this is a major thing. We need this again for the different sustainable development goals for urban development, but it also accounts for a quarter of all greenhouse gas emissions. So we have a tight coupling here between material consumption and greenhouse gases that's difficult to mitigate. We in principle know what to do. We need low carbon material technologies. We need better recycling. We need to rethink the way we use materials. And we summarize all of this in the circular economy, which is then also the topic of the standard that I want to address later. The circular economy has the idea of keeping the resources at high values. It's a no-brainer for us industrial ecologists, but still what exactly it includes and how exactly we do it is, of course, then a detailed question that needs to be mapped out. But what we can say is that we really need to monitor the growth of in-use stocks. We need to be better at recycling, and we need to redesign our products and maybe also think of new demand patterns for materials. For example, different urban forms, different cities, different building types, different transport patterns have very different levels of material consumption that can help decouple service provision from material use and later from environmental impacts. So it's a compelling concept, but it needs a reality check. Many of our colleagues do it, and famously, we have the social ecology team in Vienna who draw this Sankey diagram of the global material flow economy. It's already 20 years old, data 2005. The pattern today, unfortunately, doesn't look much different. The numbers have increased, but the overall ratios have roughly stayed the same. So we have here the throughput flows, the yellow, which is fossil fuels, the green, which is the biomass used for energy. And we have this big chunk of construction materials, the orange one, going into the stocks, into the cities. That's the cement and the steel I talked about before. And there's a relatively small flow coming out. And overall, we have something like a 30% recycling rate. So the recycling flows globally divided by the total waste flows. And the input circularity, as we call this, the recycling input rate, the recycled flow divided by the material consumption is even smaller. So we are far from being circular at the global level because the stocks grow, because the recycling isn't working as it could be. We want to broaden the framework, not only look at material cycles, but link them stronger to sustainability. And we do this with a framework, again, developed by the colleagues from Vienna, the so-called energy and material service cascade. This is a concept that was borrowed from ecosystem sciences. The ecosystem people have the ecosystem service cascade. We have a physical functioning of the ecosystem, different emergent layer of resilience and adaptive capacity. And in the end, we have the ecosystem services that have a value to people. So here in this service cascade, we link the two ends, the well-being on the left side and the ecological ceiling on the right side. That's also the two sides of the donut economy, if you know and like this concept. But we have all these detailed steps in between. It's not just one aggregate, but we actually look, okay, what happens here? For well-being, we need to meet our needs and benefits. So we need certain nutrition, we need shelter, we need access to certain services, communication, we need functioning communities, and so on. And to do this, we need stuff to work. We need driving vehicles, heated buildings, cooled buildings, working online meetings, data availability, storage, and so on. So, and this stuff needs the stocks to function. So we need the physical infrastructure to work, to be operated with energy, and then to provide services to meet our needs. The infrastructure itself needs to be built at some point. So maybe the building you sit in now was built, I don't know, 5 years, 50 years, sometimes 100 years ago. And sometimes we need to put all these materials into place. And then all of this, the materials and the energy to build up the stocks, to maintain the stocks, to operate the stocks for service provision needs to be supplied and produced. That happens here in this at the left side, the right side of this cascade. So we have these different stages, and we industrial ecologists like to look at the blue, sometimes the green stages, and of course the yellow, the material cycles in between. And each of the stages provides an opportunity for decoupling. So we can decouple functions from product stocks by using them more efficiently. For example, having more people sitting in a car. We can decouple impacts from energy by using low carbon energy, for example. So coupling can be studied at the different places, and the different coupling factors, of course, need to work together to deliver high well-being with ecological impacts under the ceiling. And we can study this cascade at different levels. So we have, for example, the process level. That's where the engineers focus on, or the process cluster level. Think of a large oil refinery or other chemical compound. But once we look at the broader picture, the product system, the product life cycle, or the material cycle, we enter the realm of industrial ecology. And if we go even beyond that and look about the system-wide, the society-wide implications, we can call it social metabolic research. So we have different layers where we can look into the material service provision, different aggregation layers, and different fields focusing on it. And we have typical indicators. That's then close to the last part of my first contribution here. We look at the typical indicators for these different levels. At level 1, the process indicators, we talk about efficiencies. So it's clear we want to be our processes to be efficient, less waste output, higher useful output. We can do the same, but now at a process cluster. So we want to have a compound of industrial facilities that again produce little waste because they reuse a lot internally. So also here, efficiency indicators are key. For the product lifecycle, it's the embodied emission. So here we have a sample. It's not complete a product system, but just there's some production processes. There's the use phase and the recycling processes. And then we can define the embodied energy as all the energy flows entering the product system, the greenhouse gas emissions, all the greenhouse gases leaving the different steps of the process for the system, and so on, really showing the whole supply chain scope. And then we have material flow accounting, for example, to look at the society level. Material flow accounting looks at the total material that our economies extract from the natural environment to process. And the lead indicator is, for example, the material productivity, total material consumption divided by total GDP, really linking physical and economic side of the economy. So that's where we are. We need to think broadly from well-being to impacts, the different stages, stocks and flows and services and material cycles. We need to look at different aggregation layers from process to economy. So how do we do it? How do we do in practice the indicator choice and link it to certain strategies? It can be done many different ways. So I want to look at one specific way of doing this, and this is the circular economy standard that appeared in 2017. So, and first, a little history about it. I wrote a critical appraisal of this standard, and I want to share the story behind this. I hope it's encouraging to you students. So I learned about this standard almost by accident. I think on Twitter, people posted about it when it was about to be released. And I said, okay, that's something that I must see, because I was eager to learn what do these standard people talk about, MFA and circular economy material cycles. And I reserved some time in my semester break in summer 2017 to go through about this. And I was disappointed because, as we will see soon, there's nothing about MFA in this standards. It's all about management and defining goals and getting the people on board and so on. And then I was frustrated because I wanted to write a review and there was no material. I could review anything. And then I said, okay, I want to overcome my frustration and say, well, if they don't do it, we need to do it as industrial ecologists. So I proposed a framework of bringing the MFA and other indicators into these circular economy processes for organization, put this into a manuscript, send it out to peer review with resource conservation recycling. Mengqing, back then chief editor, took over and said, oh, we do this quickly. After 4 weeks, I got my first review spec. After 2 weeks, I got my second review spec. And after 8 weeks, we had this published half a year after the standard appeared. So that was really a nice way of saying, hey, we can move forward fast if we want to, if we put an effort in. So we have this British standard, and it has some far-reaching ambitions in there. So what you find there is a lot of definitions of the circular economy and terms, general principle. Nothing of this is new to us. Then it links it to the management framework. So it thinks really, how does organizations work and how do they need to start about it to get something done, the different layers of the organization, and then a lot of the economic and legal issues, design issues, but not really the material issues in there. So the guidance on actually the monitoring and the indicator choice remains very vague. And from my side, I think a major shortcoming, the organizations are solely responsible for choosing the appropriate indicators. And that, I think, is not much guidance. So we need to put in the link to LCA, to MFA, and also to material flow cost accounting. So they start with, as a basis, really, if you are a company, you want to do something, they propose an 8 stages flexible framework. You scope first what you want to cover in your organization, you generate ideas of what could be done, you assess the feasibility, you develop the business case, you do the prototypes, you implement and monitor. So really management perspective, right? How do you actually do this? And then there's supporting guidance given from the bottom, right? There's a list of waste regulations you have to consider, legally, chemical regulations, and so on, logistics requirements. And wherever there are standards, they say, hey, look into this in case you need to adhere to them. And from the principle on top, there is the idea of being collaborative, being innovative, and optimize values, a bit broad management values that probably most people would not disagree, but that are hard to distill into something concrete. And then I said, okay, very nice framework, but it lacks a bit the industrial ecology content. So the first that we need to do, of course, in an industrial ecology setting is to have a system definition. So I looked at all these terms they use, the reuse, remanufacturing, and I tried to distill it into the flows we have here. So if you are, for example, a manufacturing company, then you can go to the manufacturing process and see, okay, these are the flows that I'm connected to. These are the flows that I can manage, my waste flows, my energy demand, for example. If I'm a waste management industries, I have other flows to manage. So depending on what type of organization I am, I have a certain role in the material cycles, and that should determine or dictate my scope of indicators. So this is very general. And then I went into the literature and said, okay, what groups of indicators do we have? And I linked it to the goals of the circular economy listed by the standard, restoring materials, reducing greenhouse gases, curbing stock growth, a lot of stuff that is either known in our community or mentioned by the standard that should be done. Then I suggested possible indicators, and I tried to link these indicators to the system. For example, recycling is all the recycling flows to the waste flows. This is the recycling rate, needs to be included. So really showing people which method on which part of the system should be applied to be a suitable indicator for this category. So that people on top of the management and value framework also have an industrial ecology framework to use their to implement their strategies. And then I went on to showcase from existing research how important this is. For example, a crucial limit to the circular economy is expanding material stocks. If you expand your stocks, you cannot do it from recycling. Expanding means the stuff must come from the outside. So here we have a simple mass balance equation. Every inflow of materials is either expanding stocks or it's replacing demolition, it's replacing outflow. And the ratio of stock growth to input varies a lot across countries. The red countries here for steel, they're not circular at all. If you look at Indonesia, for example, 80 to 100% of Indonesia's steel consumption go into growth, urban growth, industry growth. It must come from primary production. On the contrary, if you look at, for example, Sweden, now 10% of Sweden steel consumption go into expanding the Swedish built environment. The rest is replacing stuff that's being demolished. So a whole different precondition for becoming circular, simply because there's a mature built environment where it's easier to replace stuff rather than Indonesia, where you have to expand things. So that's really crucial. The different development stages of the built environment in country really determines what you can do in terms of circularity. Next slide, I'll skip, because to have enough time, I will then already switch to the summary. So we see that we need a closer link between the management-focused circular economy standard for organizations and the established assessment tools, especially for material cycles, but also for environmental impact tools that we have in our field. If we don't have a consistent system perspective, we have just incoherent CE indicators that different people choose. So there's a risk, and we've seen this over again and over again, that companies then cherry pick results, stuff that makes them look good, or even start greenwashing things by accounting for benefits that happen elsewhere. So we really need a proper and honest assessment of the waste flows, the stock growth in those companies. And if we deplete natural resources, if in-use stocks grow, and if the service lifetime of the products generated is short, like in fast fashion, this needs to be reflected somehow in the circular economy indicator dashboard of this organization. That means, in particular, the contribution to in-use stock growth, I think, is crucial, because this is the growth that drives primary production, environmental destruction, and greenhouse gases. So this needs to be included into the monitoring. So that's what I had to say content-wise here. Want to make use this opportunity for some shameless advertisement. If you look to our research proposal from our group, you will find more guidelines and standards in case you're interested via my contribution to the SCM section board. We helped compiling standards for MFA research, also reproducible research. We have a database being developed for material composition, for circularity indicators of all kind. We also have interactive visualization tools that are ready to use. So thank you again for inviting me, and I would be happy to join the discussion later on. Maybe now a few clarification questions and then later a common discussion after Joule's presentation. Thank you.
Sounds good. Thank you so much for the presentation. Do we have any clarification questions? I don't receive any message in the chat, so maybe not. So we can have the Q&A after Drew's presentation. Okay, Drew, are you ready for your presentation?
I am.
Okay, awesome.
Thanks so much, Stefan. I think that really is going to foster some good conversation as we go, I think. So great to be here today, and great to see that this student chapter is still thriving. That's always great to see. So as Mengqing had mentioned, I'm a professor in chemical and petroleum engineering at the University of Calgary, and I am the Canada Research Chair in Energy Technology Assessment. So my research focuses on developing and adapting tools to evaluate energy technologies at any point in the supply chain for any type of technology, whether it be conventional energy or renewable and others. In my work, the two sort of main thrusts of my work, one of them is to get better tools and data in the public domain. So releasing open source tools to allow a broader set of stakeholders to access lifecycle information to help in decision making. And those are primarily the existing systems and characterizing those better. The other side of my work is focused on developing and adapting tools specifically for emerging technologies. So I just wanted to put the caveat, I changed the title to be Lifecycle Assessment of Emerging Technologies. My focus is not on standards, but I interface with standards quite a bit, and I have quite a few opinions about standards. So I'm going to try and bring that into some of the things that I'm working on. But even just to get started, just 1 second. There we go. Yeah, so standards, I think there's a very important role for standards, not just in LCA, but in general, and they can be very helpful for specific purposes, but they will not achieve all that stakeholders hope that they will. And I think we heard a little bit about this from Stefan, that we go into them thinking that it's going to help us to get things like a threshold of robustness in our estimates, or that it's going to be consistent. And I think the biggest thing with life cycle assessment that people that are not practitioners see is that they see two studies that have been done on the same topic and the results are quite different, and they get frustrated by that. And so the knee-jerk reaction that I see in a lot of those stakeholders is, oh, well, we just need a standard. And if we have a standard in place, then we'll have, all of our studies will be directly comparable as well, right? So that we'll get around this idea of two studies going out to study these things and coming up with different answers. And so my biggest worry about the discussion about standards is that it sets an expectation for those outside of the community that we're going to be able to deliver something that is just not possible, right? I think that having studies that would all be consistent in their findings means that we don't need that many studies, and it means that we're not getting the richness out of our LCAs that we could be getting, right? So the answer to LCA is most times that it depends, and then the value of doing the LCA is to understand what it depends on, right? What are the drivers of having a result that looks at, option A being better than option B and vice versa. And so, this expectation that a standard is going to allow for all studies to be consistent is quite dangerous in terms of setting that expectation. I think there's also specific challenges for the LCA of emerging technologies. So earlier stage technologies, the ISO guidelines, the ISO 14040 series, are extremely helpful for any LCA that you go through to do. But there are some aspects of an emerging technology that actually make the interpretation of that more difficult, and that there's quite a few decisions and assumptions that need to be made specifically for an emerging technology that are not really addressed within the ISO guidelines. So it becomes even more challenging that we can't just rely on a standard to help us get a robust LCA. And so my thinking is we need to understand the role of standards, but we also need to think about alternatives that will help us achieve some of these objectives that are set by the LCA practitioners, as well as those that will be interpreting our studies. And so just to talk a little bit about the role of technology assessment. So just because I have a bit of concern about standards doesn't mean that I don't think that evaluation of technologies is not extremely valuable. So this is a pretty complicated figure. I was just trying to step through the sort of two areas of scientific breakthrough as well as technology commercialization pathways that we go through. And I would put forward that having a life cycle team and a technology assessment team can actually be really helpful for both of these processes all the way through the development. So on the left side, the scientific development, you have an observation or a question, you conduct research, you set a hypothesis, you run an experiment, you get some analysis, and very few times does that actually lead to a scientific breakthrough, right? And this is a very iterative process, as you would know. But just even getting some of the basic inputs and outputs, identifying potential applications, identifying performance benchmarks. I've been part of a sort of a conceptualization sort of activity with a multidisciplinary team, and having these sort of LCA techniques and capabilities can really help accelerate and make that process a bit more efficient. Similarly, on the technology development side, you have your research team that will come up with a concept, do a simple mass and energy balance of the process. If you pair that with a technology assessment team, you can actually start extending to the supply chain, flagging materials and hotspots, and even ranking concepts in terms of their potential promise to deliver an environmental benefit, for example. And then as you go through that development cycle, getting closer to commercialization, you can do more elaborate systems analysis to help inform those decisions. So that's sort of the plug, that even if standards are a bit challenging, there can be ways in which you can actually make use of these types of techniques even early in the development cycle. Another observation is just about the demands for LCA of emerging technologies. So how I started getting into this was I was being asked to do life cycle assessments earlier in the development cycle than the ISO guidance and most of the LCA tools have sort of been developed for. And so what I see now is that we're continually asked to do this kind of work, and we need to do it for more cases. So as new technologies and new concepts come out, we're being asked to do this on the technologies themselves, other cases that we might be interested in, as well as mitigation scenarios, so the broader system as well. And where we're seen as academics is adding value is that this is a third party, unbiased, sort of credible, organization that could help to do this assessment, and that adds credibility to the assessment that's been done, right? I see that going both ways. I see groups coming to the university asking for us to basically endorse a result to help sell their technology, and so we have to be careful about how that's done. But I do see that we're seen as a third party, sort of trusted, unbiased source of doing these kinds of assessments. We have to do it well, though, right? And so we have to look for how standards can help us ensure that we do it well. Developing and applying new methods and tools as well. So these earlier stage technologies really do require that we adapt some of our tools to address things like uncertainty. We're also asked to put this in context of more transdisciplinary research. So I'm being asked more and more to put the LCA of a new technology in the context of a particular community, and working with social science and humanities researchers who are engaged with communities to understand their concerns and their ambitions. And we can actually help to provide some of the details about the consequences of the technologies as they're discussing options. And then the education and training, right? So future LCA practitioners, but we also see that there's some guidance that's needed to the financial community, for example, where they're looking to understand the carbon risk associated with an investment, those kinds of things. And then technology developers themselves. So I spend a lot of my time working with a technology developer, helping their team to get some expertise and capacity to do some of the life cycle assessments, even very early in the development cycle. And so because of all these ways in which we're being asked to do the life cycle assessment of an emerging technology, we actually ended up creating a research network. And this is the LCA of Emerging Technologies. Right now it's hosted through the ACLCA as a working group within that community. But it started out 2017, we had an expert workshop in Banff. And this came out of conversations with other practitioners where they were also seeing that they were being asked to do these things very early in the development cycle. And a lot of the decisions that were being made were sort of ad hoc, using our gut instinct. And when we compared notes, different LCA practitioners were taking different approaches to evaluating and dealing with things like increased uncertainty. And so we felt like there was a need to actually start having a conversation within the community about this. So this was our first paper, and it was actually part of a special issue in the Journal of Industrial Ecology in 2020. And so if you're interested in the LCA of Emerging Technologies generally, that special issue is quite helpful. This one, this is one of the figures that we had in here where we were looking at even just putting the context of what is it that you're assessing, and therefore, how does that drive some of the questions that you should be asking yourself? And so we had on the two axes, not just technology maturity, the TRLs, but also the market maturity of the technology and the system in which you're thinking about doing this. And so you can have a technology that is very early stage, but it's going to be deployed in a very mature market, right? So you might be just introducing a drop-in fuel, for example. So the entire infrastructure is there, and you're just taking a technology and replacing it, something that's in the existing system, all the way through to something that is a new technology, but it also might have to define a whole new market that it might be deployed in. And so those are the kinds of examples. And so the Hyperloop travel was an example of something where both the market as well as the technology is new. And so those will drive different types of questions, different types of capacity to do the LCA and things like that. And so this, got quite a bit of traction in terms of the community receiving this as, yes, we do need to start thinking about these things as we evaluate the emerging technologies. For those that have been doing LCA for quite some time, it wasn't revolutionary, but it really was trying to pull together some of these things that we've learned by actually trying to apply it ourselves and recognizing where different practitioners will take different approaches because these things are not spelled out in an ISO standard, for example. And so I won't spend too much time on this, but I thought I might sort of try to ground the conversation in a particular example of an emerging technology that we've been using. And so these are carbon conversion technologies. And what we saw, five years ago or so was that there was a growing need to better understand and develop methods and tools to allow both industry and government to assess the system-wide benefits, feasibility, and risks of carbon conversion technologies. And so these are examples of entities that were sort of struggling to figure out what role they should play in the CCT area. And so NRC is a government agency that has a program to fund the development of new technologies, and they were struggling to understand which of these technologies might we want to fund. That similarly, Alberta Innovates and Emission Reduction Alberta were sort of in that same place. So they were looking for guidance of the order of magnitude potential impacts, any hotspots or issues associated with the technologies that might make them reluctant to sort of invest at the early stage. The Prime Impact Fund was to inform the philanthropic community as they look to place their dollars to try and make a change in the society. How might they think about these new technologies? And then the last one is the X Prize. So this is an organization that tries to set up big prizes to try and help advance a technology in a certain area. And so they had two test sites, one in Canada, one in the US, where they were actually encouraging teams to actually come through and demonstrate that their technology could convert CO2 into a value-added product. And they had to hit a certain sort of magnitude of, can you get to the next level, take it out of your lab and do it at sort of a pilot stage. It wasn't quite commercial, but it was at least a pilot stage to demonstrate that these technologies could work. And so different types of stakeholders that were interested in this. This was a team of folks from universities across Canada that were trying to look at this to try and understand this better. And so this part of the reason why this is a good example of where we need to think about what do we standardize, how do we make use of standards, and then how do we think about other tools and methods that might be needed. And so one of the biggest issues here is just the number of pathways and the disparate products that would be produced through these processes. The other thing to say is that there's a whole range of different technologies that can convert CO2. Each of those technologies are at different stages of development. So some are just at the concept stage, some at the experimental lab stage, and some are very close to commercialization. So you can see here that where you get your CO2 from is important. The next set is the categories of the first reduction of CO2 or the conversion of CO2 in the first step. The CO2 reaction step, so what you're actually doing, the mechanism by which you're converting that CO2. And then on the far right is all of the different main products. And so we had data from different technology developers through this larger project, and we ended up with a combination of different steps in these processes that led us to 97 different pathways to assess within these categories. And you're trying to make comparisons between something that would generate a fuel like diesel fuel or a synthetic diesel fuel and comparing that to a methanol fuel, which we don't really have a definition for use in transportation, right? That's not a very established market, so you're much more uncertain than trying to plug it into a diesel market. And then you're comparing that to chemicals for different purposes, as well as materials, right? So very disparate sets of applications of these pathways. The ISO guidelines really don't help you get your head around how to structure the analysis for all of these different types of differences. And so we set up this generic process flow diagram. We went out to technology developers and others to actually calculate the life cycle impacts associated with each of these technologies. But what we also found was that we needed to think about different functional units to make these comparisons across these different types of products. We had 4 different environmental evaluation metrics. I'm showing the examples for CO2, but obviously you could extend this to other environmental impacts, which is really important as you go through the different types of pathways that you might be interested in. So the first one is just looking at the amount of CO2 that actually gets emitted to the atmosphere for every kilogram of CO2 that you convert, right? This allows us to make the fair comparison across all of these things, regardless of the function that they're actually providing. The next one is the product base. So, you could go into the transportation fuels subset of these pathways and say that you want to look at the CO2 that's emitted for every kilogram or megajoule of product that is produced from this. And then the avoided emissions are that difference between the emissions that come from your pathway compared to what you're doing today, so the incumbent pathway. And then the fourth one was understanding what the climate impact could be of these things. So if you did scale it to a large portion of a market, how much impact would it have from a climate perspective? That's also important to understand what the potential of these technologies are, right? You can imagine that a philanthropic organization is looking to have a big impact on the climate. And so you might have something that is much lower in emissions than the incumbent technology, but if it's only a niche market, you're not going to have a very large climate impact, for example. So that was the fourth metric. So just for the X Prize, as an example, we were looking at different pathways. So one of them was mineralization. So there were multiple companies that were taking the CO2 and converting it into a mineralization product. So either producing concrete as a substitute, or actually augmenting that concrete production with CO2, those kinds of things. And so these are the greenhouse gas emissions per kilogram of product. There were multiple products that came out, so it wasn't just one generic specification of concrete, for example. And so the kilograms of CO2 that are emitted per kilogram of the final product that was produced. And on the left-hand side graph, we're looking at each of the individual stages of the life cycle emissions. The blue are the performance of the technology at the test site. Right. So a lot of times these are professors that are working in the lab on a technology. They've created a team that's going to take, they've started up a company, and they're going to take that team and try to actually scale that technology and operate it at a test facility. You can imagine that at that stage, many things go wrong, right? Many things are not optimized in the system. And so the blue are the actual test center performance. And we did a median across the different companies. And then the orange color is where we gave them a chance to say, okay, you had to use diesel as your input energy fuel source for this process. But, you know, in 2030, if you were actually commercializing this technology, you would have found another source for that energy input, and it would be lower carbon. So what could you envision changing about what you did at the test center to say, okay, here's where we think we could get to in the 2030 timeframe. And so these, you can see the comparison between these two. On the right-hand side, we had to show the net emissions because a lot of these companies were claiming that their technology was net negative. And that was mostly a boundary issue where they weren't actually defining it across the full life cycle. So we wanted to show that the net emissions of the technology are anything but negative, right? You can see that on the left-hand side, we have the CO2 feed, and there was a credit assigned because of the way that the X Prize was set up. It's not guaranteed that you're always going to get that credit for a feed if it's a technology or a facility that needs to be sort of decarbonized, shut down, replaced with a lower carbon source. But if you did get credit for that, that would be the only part that would have negative emissions. The rest of the life cycle is positive. So the net effect is that you're not going to have a net negative emission technology through these pathways. And then, but you can be better off than the incumbent technology. So that's where the net incumbent was there as well. But that net incumbent is also decarbonizing. And so you have to actually take that into account when you do that comparison as well. So that's the kind of thing that we used to sort of educate the judges that were making the $15 million decision about which of these technologies that we needed. And you can see that we needed to tease out more details than maybe you would typically see in a life cycle emission result. We also went to our, traditional tornado plots to show them what it depends on, right? How would these pathways change in terms of their emissions? And you can see even a mineralization pathway that isn't dependent on electricity as the driver, which you would see in an electrochemical process, for example. It's still heavily dependent on where you get your electricity from. And so we used a low carbon grid and then a higher carbon grid as examples for that. And so we can help the judges understand the conditions under which they might see these technologies being more or less competitive. And so this was used then to inform that judgment. But if we step back and think about the standards, the ISO guidelines would not get us to the place where it would have helped us inform every one of the assumptions and decisions that we made, the way that we communicated those results, and so on. It's a great starting place, but it wouldn't have helped us get through all of these details. So just the last piece then, I was going to tell you about a paper that we're working on. So as part of this network, our current paper is under review at the Journal of Industrial Ecology, and we just recently got some really great feedback from reviewers on this. But basically, we took a Faraday-style approach to this work. So it's a slightly different approach. Faraday was 150 years ago or so, used to actually collect the papers in a very specific field of chemistry, and experts in that field would review what had been published that year, and they would sort of debate what that meant about the direction of the field. They would identify where, they would document all of their discussions and identify where the community might diverge in their opinions and where there was consensus in terms of where they thought the field would go. And so we've been doing that as a group since the Banff workshop in 2017. And so we wanted to use this as an opportunity to sort of show where we're still not getting full consensus and where there are challenges in doing LCA of emerging technologies that really needs more discussion within our community. So we looked at, where there are tensions, divergent views, and unresolved questions in the field. And part of that, you'll see, is associated with standardization. And there is a preprint there, the link there, so you can actually see that. We are in the process of revising right now. But here we identified 6 different areas that we found we didn't have consensus on. And so appropriate use of LCA. So even when do you use LCA and when do you call it LCA, right? If it's just a concept stage and you're using life cycle thinking, does it do a disservice to the work if you call it an LCA, and then people might interpret it that it's sort of definitive, conclusive results that might write off a whole category of technologies, for example. So that was one of the discussion areas. Obviously, uncertainty is always a discussion point in LCA, but it's a more prominent thing in emerging technologies. And so one of the big points of divergence is when you have higher degrees of uncertainty with an emerging technology, is that the place where you lean into the more sophisticated uncertainty techniques, or is that the area where you acknowledge that you're doing order of magnitude calculations and you just want to present it as a rough estimate, not a something with a very finessed distribution that implies something that maybe we aren't ready to actually say conclusively at that stage. The comparison to the incumbent, so I didn't get into a lot of detail about the incumbent that was assumed for the X Prize, but we did assume something about what we're doing today to produce that product. But I might pick something different than somebody else, particularly in different regions of the world. And so comparison to the incumbent is also an important factor. Standardization was there, and it is a hotly debated topic. One of the most interesting things about standardization, I think, is the what is it that you want to standardize, right? Is it that you want to standardize the methods and assumptions that are made? Do you want to standardize the data that's used? Or do you want to actually standardize the practitioner that's there? Is there a way that we could explore getting credentials for folks that ensure that they have the training that they need, that they're going to make reasonable assumptions, up for discussion. How you scale the technology is also very, challenging. I think it's a ripe area for new research in terms of taking something that's at a technology readiness level of a 3, so very early stage. How do we take that data and use it to envision what we might see at commercialization? And then the stakeholder engagement piece is we're being asked more and more to get involved in stakeholder discussions, but we don't have a lot of mechanisms by which we can actually bring different perspectives and different ideas into the LCA process. So I won't spend too much time on any one of these. We do have sort of discussions and visuals for that in the paper. I'll just highlight the standardization piece. So some of the open questions we were left with after lots of discussion was how could or should additional standards beyond the ISO 14040 play a role specifically for emerging technologies, and then how to develop fit for purpose standards as well. And so this is sort of the way that we tried to visually represent that. And so on the x-axis is the technology stage, right? So the technology readiness, is it a concept or is it a commercial technology, and that spectrum of developing the technology? And then on the y-axis is just how valid is each of these statements, right? So the bigger the height, the more valid it is, right? So on the commercial side, on the right-hand side, the ISO 14040 series, when you're at commercial stage, that's sort of what it was designed for. So it's highly applicable, right? And not that you shouldn't use it for every stage of the technology, it's just that it's very applicable at the commercial stage, and it goes a long way to helping you get robust results. That's not as true when you're at the concept stage, right? If you go all the way to the left-hand side, that if you have something that's standardized that said that I followed the ISO X series, you might imply and generate overconfidence in your results, right? So complying with the standard is not a proxy for robustness when your data is so scarce. And so the other thing that we highlight here is that there is an area for additional standards that could be helpful as that technology develops. And then we have the industry-specific standards that already exist and could be developed further. And I think the circularity standard that we just heard about, building some of that out to specifically focus on those LCA metrics could be a really nice enhancement to that work. At the top, we just have some considerations, some things you should ask yourself as you go through this process as well. And so what we learned is that, standardizing LCA of emerging technologies offers opportunities, but also risks, right? So you can reduce the ad hoc nature of current methods decisions, but you might also generate this overconfidence in the accuracy and comparability of the results by saying you followed a specific standard. And then we're still left after all these discussions with, it's not quite clear what could or should be standardized associated with this. So moving forward, though, definitely encourage people to make use of the ISO guidance as much as possible. Nothing that we're doing sort of defies the guidance that's given, so we're not contradicting anything that's in there. So always start with that. But in the absence of additional guidance, where we would suggest is that you actually lean into being transparent, right? So actually document all of the assumptions you're making, so that people can understand where the limitations of the work are, and they can take the results at the appropriate level of conclusiveness. And so the proposed next steps then are to further discuss as a community what could or should be standardized, as well as alternative guidance opportunities that we could give, and then continue development of standard sets of narratively consistent future scenarios. That's one thing that we did land on, that having some of those future scenarios that are internally consistent. If you are decarbonizing, then you need to decarbonize your background system as well as the incumbent that you're comparing to, for example. These are some of the other ones. I'll just leave with what I started with is that we do agree that the standards can be helpful, but we need to be very thoughtful about the way we think about that, and that the alternatives should be explored, right? That's something that alternatives to standards to support those standards as well. And so just as a plug for our next paper, I'm guessing that most of you weren't even born when this paper was published by Wiedema in 1996, but it's the data quality, the pedigree matrix. Hopefully you're familiar with its iterations and things like that. But this is a structure by which you can actually start assessing the quality of the data that you're using. What we're thinking about doing is actually expanding that to other quality parameters, so that when you take a study that's at a sort of concept or very early stage, that you can articulate enough detail about the quality of not just the data, but the assumptions, the system that you're building, the background versus foreground, all of the assumptions that you're making, that you can actually articulate that so somebody can better interpret how conclusive your results are. So that's our current work that we're working on. I will just say that we do have students and postdocs participating in this working group. So Rachel Woods Robinson is the lead author on the paper that we're currently working on, and she's a postdoc at the University of Washington. So I'll leave it at that. I have my email address here if you're interested in hearing more, you want some of the details and things like that. But I do look forward to the discussion. So thanks very much.
Thank you, Joule. Wonderful presentations. Very interesting to see like two totally different perspectives, but also all of them are very important concepts. I don't see anyone raise their hand, so I guess I have a privilege to ask questions in my mind. Yeah, well, I think I have a question for both of you. For Stefan, I have already put my question in the chat. So I really appreciate you shared your story, the story about behind the paper. I really like that part. So I think my question is, in your experience, what are the main challenges like those organizations face when trying to, apply or implement those circular economy indicators or standards?
Yeah, thank you, Mengqing. I would say different ones. First of all, there is a system boundary question. If you have a product, how far do you extend the system boundary? Is it the recycling after this you want to factor in? Is it the stuff that happened before with the material? So we have seen LCA studies that actually traced material through different life cycles and try to develop indicators for it, which is nice from the product perspective, but it's also across different companies. It's not unclear what the contribution of an individual company is. So life cycle boundaries, system boundary is one thing. The other one is, what indicators to choose, right? If you want to basically also have a marketing perspectives always in the background, you want to be seen as a circular economy indicators. So indicators that almost by definition don't make you look very bad, maybe are sorted out from the first place. So this is a challenge, to be honest enough. Data availability is a challenge. Often the material flows are monitored, but not so much the material quality, which is crucial for circular economy to assess the value properly. And finally, of course, to link those indicators to the actual business model, right? Just because you have an indicator doesn't mean that certain company parts can act towards it, right? It also needs to fit into the business model logic to create appropriate incentives. So these 4 points, I would say, are the challenges.
Yeah. And also, I think a follow-up is in your paper, there are many different indicators you propose, right? Relate to efficiency, MFA, LCA. I wonder, and I assume when you apply different indicators to the same case, the conclusion can be very different, right? Do you have any examples in mind? Are there any examples showing different conclusions when applying indicator A versus indicator B?
I mean, we have different conflicting impacts, right? For example, if you switch to anything that's electrified, you go down on the carbon emissions, but you increase the material footprint because you usually need more copper in larger quantities, which have a huge material footprint. So we have this stock growth thing, right? To go low carbon, we need to increase our metal stocks, and that really drives up metal consumption. And at least for the time being, is not circular because we need to increase first. Plus, that many minor metals, technology metals, have very low recycling rates. So that's a major trade-off.
Sounds good. Thank you. Any questions from the, okay.
I also have a question for Stefan. Sorry.
And now the
Maybe-
questions are coming
Yeah,
slowly.
maybe a bit stupid question because I think you did mention something about a standard about LCA, and you mentioned in the standard you read and you did studies, they don't have anything so much thing about LCA or MFA. Do you think there also should be a standard specific for MFA, include a system boundary or something like that?
Yes, very much. And it starts that MFA has stock versus flows. Not even this is properly accounted for, but also the question at which point do we measure material flows? It's crucial, right? And should be more consistent. Is it, for example, the waste flows before or after trade, material consumption before or after trade? Obvious stuff like dry mass, wet mass is sometimes not clear. So definitely more standards are needed for accounting at different levels.
Yeah, thank you.
And sorry, one more quick thing. Even worse, when it comes to indicators. So the accounting, I mean, people can understand, but it happens so often that you get an indicator recycling rate, and it's it's something divided by something else, but it's nowhere documented what are the actual original flows behind those indicators. So that's often frustrating, trying to understand percentages because you don't know what the basis is really.
Yeah, I agree. Yeah, thank you.
Yeah, we have a couple questions in the chat, so I'm just gonna read the question. So there's one question, I guess, for both of you. Say, hi, thank you for your great presentations. What are your thoughts on the role of policy and regulations as an additional layer to LCA standards? Do you guys have any thoughts on that?
I can talk about the California low carbon fuel standard and the clean fuel standards in Canada. I'm not sure if those are the types of regulations you're thinking about. I think that once it gets in the hands of policy and policymakers and regulators, the concepts of LCA sort of go out the window, right? And I think it has really driven action in terms of looking for lower carbon sources. But I wouldn't say that it would stand the test of any sort of ISO guidance or anything else, right? And what I found a lot of times is that there is like a political compromise that's made, that you take the LCA results and then you put it into a form that is politically palatable. And so I think that is a challenge, right? I think the other thing is that a lot of the regulators, somehow we've set the expectation that our LCA results can be reported to 4 significant figures with no uncertainty, right? And so that also makes me uncomfortable in the way that those things get adopted. So I think it can drive change, and I think it's really important for LCA practitioners to make sure that the regulators are aware when they're making those compromises, so that they're explicit, and that they also look for the unintended consequences that can come from that, right? So like both of those two fuel standards, they stop at the megajoule of the transportation fuel, right? So that in itself sort of has issues. It's also they don't necessarily take like refining intensity into account in these things. They sort of treat that as a separate, well, in California anyway, they have a separate policy for refineries that disconnects things, and where the value of LCA is the connection across the supply chain. And so I think it's compromises that we as LCA practitioners are not happy about, but at least even thinking through the life cycle approach is helpful in navigating those regulations. The attention paid to the unintended consequences of sort of chopping it up and making those compromises needs more attention.
Thank you, Joule. I'm not sure if the person who asked the question has any follow-up. Well, Stefan, do you have anything to say about that question, or we can move to next question?
Quickly, another example, in the European Union, we have now mandatory recycling quotas for some products. For example, car manufacturers need to document that 95% of their end-of-life vehicles are actually sent back to recycling. So that creates strong incentives to not only focus on steel, as it was previously the case, but also on other materials. So that more or less is really pushing for circular economy in some sectors. It helps with recycling the bulk materials, not so much the specialty ones that they need other incentives for, but it really pushes the product design and the waste management industries.
It's going to be challenging. There are so many different materials, right? For the car transportation sector. I remember I did a research tracking the plastic use in transportation sector. I found the data is lagging. I have no idea how people are going to achieve the recycling quota. The 95% sounds a very, very ambitious target.
And there's always loopholes. I don't know the details. I wouldn't be surprised if energy recovery is okay for plastics because of the high diversity and low recyclability, but I don't know the details. But
yeah, it's also really how you define the concept, right?
Exactly, what still counts as recycling.
Right. Yeah, so related to the concept, I think we have one question in the chat. They want more clarification about the definition of well-being. So the question is to Stefan, I have a question to the definition of well-being. What if achieving well-being ends requiring too many resources? Just to play with the concept of, yeah, I'm not sure if I understand that question.
Yeah, thank you, Ursula. Well, if high levels of well-being still require too many resources, we have an overpopulation problem. And we have it in some regions of the world. It's not new. In previous society, the agricultural society, this was often the norm. These were typically overcrowded societies with relatively low levels of well-being. I mean, today we can be optimistic. A lot of research, if you think of the contributions by Julia Steinbergers and others, have shown we do have the technology, we do have the means, the production means, and the recycling to really decouple well-being from resource use. I think it's more a distribution problem at the moment than an actual scale problem. It's really the inequality that drives up consumptions way beyond decent levels of consumption and well-being.
Sounds good. I will also have one question for Joule. You mentioned that there are different environmental evaluation metrics like pathway-based, product-based, yeah, so I would imagine the conclusion can be very different when you use different functional units. So my question is, are there any guidelines like an ISO guideline give us what would be the most appropriate functional unit to this question, where it really depends on your research question?
Yeah, I can't remember the exact language, but my philosophy about the functional unit is that ideally you always want to go closest to the actual service that's being delivered, right? So that's where I was critiquing the California Low Carbon Fuel Standard, because they stop at the fuel, they don't actually go to the combustion and use for the transportation service. So per kilometer or per mile would be the better functional unit in that case. And so there's not hard and fast, and I don't see any discussion about potentially needing to have multiple functional units, right? Like, I think for the CCU case, because it is so complex, I think you need multiple, right? And that's okay to have more than one functional unit, but how you determine that and how you determine which of those functional units would be helpful for your research question, there's not guidance associated with that. And that's the kind of example where for emerging technologies, it might be even more relevant to explore the use of multiple functional units, because you might, even for one technology, you might have different downstream paths that it could connect into, so different markets. And so, I think there's lots of examples where additional guidance when you're thinking about an emerging technology can be helpful.
Exactly. Yeah. Thank you. Not sure if we have more questions. I think I have a very general question for both of you. Well, I think a lot of people here in this webinar, we are kind of like a junior researcher where we're doing our PhD or master in graduate school. So we are kind of wondering, for both of you who are more senior than us, you have so many more experiences doing research. Do you have any advice for junior researchers? I know this question is quite broad. Yeah.
I guess as Stefan was answering and talking about the recycling outcomes that come out, I think that's a great example. I think I've seen in my path, as well as for other students, that you can get discouraged when you do this really careful analysis, and then the policy evolves in ways that aren't as informed, or it gets taken over by things like politics. And I would just say, you can't control everything, but there's still a lot of value in doing the LCA work that you're doing, right? So don't get discouraged if at the end of the day, the politics sort of take over and maybe end up in a place that you wouldn't recommend from an LCA perspective, because doing the LCA, like, one of the things I find as being my biggest contribution is just reducing the rhetoric that goes around as you go forward, right? Putting better data and tools in the public domain, make it harder for people to sort of twist the numbers in ways that serve their purpose. So there's still a ton of value. And I would also just say that that doing LCA earlier stage all the way through, it just continues to gain momentum, right? People in government, but also in companies, are really looking for this expertise. And so I do think that you're in a growing field. We can also see that with the ISIE, as we were talking about before, like, it's a growing community, which is great. I think that you're in a really great place moving forward in your career, whether you stay in academia or go to industry or government.
Yeah, you mentioned a very important point, because I'm also doing some research related to policy. I'm also, in the back of my mind, I'm worried about the policy will be withdrawn. And then my research gonna be like no meaning at all. Yeah. Thank you. Stefan, do you have anything to add?
Yes. Well, first, I can only second, Joule, what you said, right? I think focusing on high quality research that's transparent and reproducible is our core job. It helps, it's more satisfying, it's well recognized, it's more cited, people will build up on it, it helps build your reputation. And the other one is, because it can be frustrating to work as a sustainability scientist, Joule, for the reasons you mentioned, I think it's crucial to be to reflect about your own values and how they link to your research. That reflects both the topic that you do, the method you choose, but also how you see the science-society relation. Some people are more on the activist side, some people are more distant, but you could do transformative activities in your spare time or others. I think just reflecting on having, I think it's a long-term healthy balance. If you know what your values are, that your work and also your focus aligns with your values, and also the way you see your work contributing at the different levels, right? From data supply to method development to actually sitting down with policymakers and get, even if they just try to convince them to include copper in some standard or some, so many different things are possible here. So reflect on that to be sure what you do is consistent with your values.
Thank you, Stefan. Can I just add one thing? I think I came into this research sort of in a circuitous path, as most people do. And it was always focused on trying to improve environmental issues. I've ended up working a lot on fossil fuels, which was not what I intended to work on, but it was an area that was really understudied. And that, reducing the rhetoric about claims that are made in the existing system, I think, has been a focus of mine. And so, but working in this space, it's really easy to get discouraged just generally in terms of progress on climate issues, that kind of thing. And one of the things I learned very early on from a professor actually at the University of Toronto, who had been working on air quality issues and just felt like the policy wasn't catching up, that we weren't making enough progress. And he just sort of gave up, I felt like, right? And so for me, that was always my inspiration is despite what's happening, despite lack of progress, putting effort into maintaining your not unbridled optimism, but keeping some optimism there that, you can make a difference, right? I think is really important. And you have to work hard at that, right? Because it's really easy to get so discouraged that you feel like you're not going to make a difference, and therefore, why should I bother? So be conscious about that as well as you go forward.
Great, awesome. Thank you so much for, I got more motivations now. I think just trust myself, trust our research and meaningful, and have this group just encourage each other. That's good. Okay, so it's 12:15 my local time. I think we're good for now. So we don't have more questions. And I just want to thank you, Stefan. Thank you, Joule, for your time, contributing to this student webinar. Your presentation, very, very meaningful. Thank you so much.
Thanks. It was a great discussion.
Yep.
Good luck to you all.
Mengqing and Jaja for organizing. Thank you. Also, Joule, for showing the cogwheel diagram.